Howdy. The purpose of this video is to go into detail on the lever rule. How do we find out concentrations of phases present from a phase diagram? The lever rule basically allows us to calculate that. It's based on a mass balance assumption. So we're going to demonstrate it, and then we're going to go into the derivation, and finally we're going to do a sanity check to make sure everything makes sense. I always like to start off with a fairly complicated phase diagram just to remind you that anything that we go through in this case is perfectly applicable to a more complicated system. Having said that, we're going to start off with a little bit easier system. So again, this is a binary isomorphous phase diagram. Now we use the lever rule when we want to know what is the concentration of the different phases present. So how much, in this case, how much solid alpha and how much liquid is there? Sorry, liquid. And the phase rule, the lever rule, allows us to calculate that. So let's do an example. Let's say the bulk composition or the system composition is well, it looks like 40% B, component B. As a side note, sometimes this is called bulk, sometimes it's called the system, sometimes it's called total or the whole. In all these cases, we're picturing a system being a box that we have some material in. We want to know what is the composition of everything in that box. Okay, at some temperature up here, we are in the two-phase region. And so the first thing that you want to do when you're in the two-phase region is draw a tie line. And this tie line is going to give us important information. It tells us what is the composition of the solid present and what is the composition of the liquid present. Okay, in order to apply the phase rule, we need all of these numbers. So this liquid looks like it's about 50% component B. The solid, maybe just to do the math easier, we'll say it's about 30% component B. Okay, so to apply the phase rule, I need to know three things. I need to know this overall length, I'll call that C. I need to know this length, I'll call that A. And I need to know this length, and I'll call that B. So in this case, A is given by the difference between the system and the solid composition. And so we usually look at the absolute values. That way we don't have to worry about signs in this case. So the system composition I said was 40%. Let's start to use fractions or decimal fractions, because that's a little bit easier. The system is 0.4. The solid composition is 0.3. So A equals 0.1. Okay, what about B? In this case, B is 0.5 minus 0.4. That is, it's the liquid composition minus the system. So B is the length from here to here. And that also equals 0.1. Finally, C is this overall difference. So C is the composition of the liquid minus the composition of the solid. And so in our example, that's 0.5 minus 0.3 equals 0.2. So if I'm applying the lever rule, I'm asking how much is there of some particular phase. So let's ask the question about the liquid first. So how much liquid? In this case, I would take the fraction A over C. And so using the numbers I've calculated here, that's 0.1 over 0.2. And so there is 0.5 or 50 weight percent, mass fraction, sorry, of the system is liquid. How about the solid? How much solid is present? That's given by B over C. Again, that equals 0.1 over 0.2, 0.5. So what I've said is for these numbers, there is 0.5 mass fraction of liquid and 0.5 mass fraction of solid phase alpha present. That's about right because this line is about in the middle of my composition. In reality, this number probably was a little bit higher than it should have been. But this is how we apply the lever rule. Okay, let's talk about derivation. Where does the lever rule come from? I told you before, it's related to mass balance. So let's look at a system, and again, at some composition of the system and some temperature. And again, let's use these terms that I defined before. What is the composition of the solid, the composition of the system, and the composition of the liquid? So I will say X solid, and this is in terms of B. I could do it in terms of component A as well and get the same exact answer. X liquid and X system. Okay, let me also define a couple other variables, and I'm going to use W for a mass fraction. How much mass, what is the mass fraction of phase alpha, and what is the mass fraction of the liquid present? And I know that the mass fraction of these two added together equals 1, right? Okay, so what does the mass conservation tell us? Well, the composition of the solid, just to be consistent, we're going to use alpha here. The composition of alpha times the mass fraction of alpha plus the composition of the liquid times the mass fraction of the liquid is going to equal the composition of the system times the mass fraction of the system, which is just 1, right? So this is basically a mass balance equation. Okay, I can substitute this relationship in for either of these two variables. Let's say I replace W sub alpha with 1 minus W sub L. So the mass fraction of solid present equals 1 minus the mass fraction of liquid present. So I'm going to substitute that back in here, X alpha B. And, right. Okay, so I'm going to get something like this. Now, the next steps are basically simple algebra, but I want to solve for W sub L, right? The whole purpose of this is to calculate the mass fraction of liquid or phase alpha from the compositions of those different phases. And I encourage you to work through this yourself, but what you'll find is the mass fraction of liquid equals composition of the system, put absolute value sign here, minus composition of alpha over composition of liquid minus composition of alpha. And again, this is all relative to component beta. I could repeat this calculation for component alpha and get exactly the same result. And this is this ratio that we used in the previous figure. So system minus alpha, again, this is alpha here. So system minus alpha is this distance. I believe we called that, yeah. So we called this A. Liquid minus alpha is the whole length. So A over C. Okay, so this is where the lever rule comes from mathematically. Some people like to see that derivation. The final thing we're going to do is just a quick little sanity check. And I encourage you always to do this when you're when you're asking questions about concentration of different phases present. And so I'm gonna, just to make sure I'm getting the point I want, I'm gonna start up here. Let's say my system composition is this, and my temperature is this. Again, the first thing that I always do if I'm in the two-phase region is I draw my tide line. Okay, now you can notice here's my composition of liquid, here's my composition of alpha. So the composition of the overall system, in this case, is a lot closer to the composition of that liquid phase. So for the only way for this to make sense, there needs to be more liquid than there is solid. So think about that for a second. If the composition of the system is closer to the liquid case, there needs to be more of that liquid present. So when we look at our different lengths involved in the lever rule, I drew this intentionally so that A is significantly longer than B. And remember, the fractions are either A over C or B over C. And the most common mistake that students make is mixing up which one of those refers to how much liquid is present and which one refers to how much solid is present. But remember what I just said. I know that there's more liquid present in this case. And so A over C, you can tell just by looking, A over C is going to be larger than B over C. And so A over C refers to the liquid. So I would call this a sanity check, right? Look at the system. See if the ratios that you're calculating make sense. These should always be, if I'm calculating fractions, it should always be between 0 and 1. And whichever phase I expect there to be more of, in this case I expect there to be more liquid, that's going to give us, that one is tied to A over C, which is a larger fraction than B over C. Okay, we did it with a fairly simple phase diagram. Let's do it with a more complicated phase diagram. Let's say I'm here at 70 weight% copper. And let's say I'm looking at this temperature, 700. So I can follow that across, I can follow this up, and I get a composition of the liquid. So X sub L is about 0.62. I get a composition of a phase epsilon 2. And that composition looks like it's about 0.75. And my lever rule is composed of C, A, B. So if I wanted to ask how much liquid is present, the liquid in this case is going to be given by B over C. It's the opposite side of the lever over the total. Before I used W sub L to stand for this. And so I could calculate that, right? B is 0.75 minus 0.70. C is 0.75 minus 0.62. Always make sure that this comes out to be a positive number because a negative fraction doesn't make sense in this case. And so if I calculated that out, that would give me the weight fraction of the liquid. So all of this, all this stuff we did for the very simple isomorphic binary phase diagram is perfectly applicable to a more complicated phase diagram as well.